Let us start lecture 48, and the course is on phase diagrams in single component and binary systems. And today's topic, it will be to understand del Hmix as well as del Gmix in case of solution which deviates from ideality. So, it is basically the continuation of discussion what we have done in the last lecture. So, in the last lecture what we have found out that at a particular temperature and pressure, so for binary solution of A and B, where A, B have the same crystal structure and the solution also has the same crystal structure, and we are talking about 1 mole of solution. We have seen RT, or we can talk about G2 is nothing but XA GA bar plus XB GB bar, and this is G2 is for solution, which can be applied to for both ideal as well as non-ideal. So, when we apply it to non-ideal case, so we see that GA bar equal to GA naught plus omega 1 minus XA square plus RT ln XA, which can be also written as GA naught plus RT ln AA, and another one which is GA GB bar equal to GB naught plus omega 1 minus XB square plus RT ln XB. It can be also written as GB naught plus RT ln AB. And from this two equation, we have seen that AA divided by XA equal to gamma, which is a constant when we talk about when XA tends to 0, XB tends to 1, and the another case AB XB equal to gamma, which is this is A, this is B, which is also constant when we consider XB tends to 0 and XA tends to 1. Okay. So, these are basically Henry's law. Now, if you recall, when we have plotted this Henry's law considering activity, that time we considered gamma A and gamma B to be a constant term, but now here it is proven why it is constant, and now we can actually express, we can actually plot that and show that how this two equation would be expressed graphically. So, if I do it for XB, let us say this is pure B, that means XB equal to 1 and XB equal to 0. So, this both ends, and we know, and this is activity term, and this one would be equal to 1 activity of B equal to 1, that is the pure side. So, if I talk about ideal case, it will be a straight line, this is ideal solution or Raoultiel solution. Now, here if I try to, so that means we have to look at this part in this case. So, if gamma B, now from here we can actually see that gamma B could be greater than 1 or gamma B could be less than 1 if it is having Henry's law fulfillment. So, then we can, if it is gamma B less than 1, I can, this is where activity of B is less than activity of B when it is ideal, and this is nothing but XB ideal. Okay? And this particular equation will be expressed here. I have to draw a straight line or the tangent over this activity plot with composition when XB tends to 0. So, this is my XB, gamma B is constant and it is less than 1. Similarly, I can have a plot for a situation when AB for non-ideal case is more than the AB, A means activity of B in case of ideal. So, we can have a plot like this. Okay. So, this case AB is more than AB ideal, which is nothing but XB ideal. Okay. So, similarly here also I have to draw a tangent when XB tends to 0. So, this is gamma B equal to constant and greater than 1. Okay. So, that is the condition we are getting. So, though with respect to B we are considering, we can also do it with respect to A. So, in order to do it for A, just to combine them together. So, let us say this side is pure B. So, which means that x b equal to 1, which also means that x a equal to 0. So, now we are putting everything in perspective of x a. This is x a. So, here x b would be equal to 0. This is pure A and x a equal to 1. So, here I am putting A, activity of A. So, we can have a activity of A equal to 1. So, and then we can join this straight line, which is nothing but ideal solution, and in this case it was B in A and in this case it is A in B. So, now if gamma A, so that time we have to consider this equation in case of solution of, if gamma A is less than 1, okay, so then that plot would be like this. So, this case, this is gamma, or we can say activity of A should be less than activity of A when it is ideal, or we can say less than x a ideal. Why? Because gamma A in case of ideal is equal to 1, which is that straight line. Now, in order to have that Henry's law fulfilled, we have to draw a tangent when x a tends to 0. So, it will follow up a tangent over this plot here. So, this is gamma A is equal to constant and less than 1. And for the other case, which would be for, and this case A is greater than A ideal, which is nothing but x a ideal, since gamma is equal to 1, but Henry's law fulfillment would happen here. A tangent over this activity plot when this one was basically gamma A is greater than 1, and that time it is also a constant. Okay. Fine, which is the slope of that straight line, both the cases. So, like that we can operate why gamma becomes a constant at a very dilute solution, in case of a dilute solution. Now, taking this forward, so we have seen that G xs is nothing but delta H mix, which is nothing but omega xa xb. So, if you find this value, it will be in the form of joule per mole. Joule per mole. In fact, this equation can also be written in terms of RT alpha xa xb, and alpha you can think of a constant here. It can vary for a particular condition, particular configuration, let us say. Okay. For example, omega, it can have different values for a particular solution as per the interaction of bond energies. So, this alpha is also related to that, because omega is nothing but N0 Z EAB minus EAA plus EBB by 2. So, this particular contribution that is coming due to the differences in bond energies, that is omega. So, then alpha is also related to those bond energies, but only advantage would be this omega, we can then from this we can write that alpha is nothing but omega by RT. So, in that case this alpha can have a very small value, and accordingly we can actually have a kind of a simple plots of del H mix as well as del G mix. So, this alpha can have a value from 0, 0.5, 1.0, 1.5, like that we can go ahead. Okay. But otherwise if we go with this omega term, it will have a large value. So, in order to simplify that, so the alpha is considered. We see that delta G mix is equal to delta H mix minus T del S mix. We can write xa delta G A bar m plus xb delta G bar m b, and you know these are the partial molar quantities for the formation of solution of A in AB as well as B in AB solution. So, that is the mixing partial Gibbs free energy term. Now, once we write that, then we can actually get an information about this quantity as well as this quantity from a graphical means. RT xa ln AA plus xb ln AB, activity of A and B. Now, so that means delta G bar m A equal to RT ln AA and delta G bar m B equal to RT ln AB. So, we are getting these informations. Now, if I try to see del H mix, which is this quantity, this one. So, it can let us take two considerations. One is let us say a small positive, and another case, this is case 1, and the case 2, let us take delta H mix is small negative. Okay. So, this is small positive and this is small negative. Let us see how this del H mix plot can be shown on del H mix versus xb, or the mole fraction of B or A. So, we can plot, if I plot, let us say this is 0 0, since this is equal to this quantity. So, x a equal to 0, del H mix should be 0, x b equal to 0, del H mix should be 0, and this is parabolic and symmetric between these two 0 term, and this 0 is coming because here x b equal to 1, which is pure B, and here x a equal to 1, which is pure A, and correspondingly x b equal to 0 and x a equal to 0. Okay. And we are putting x b is increasing this way. So, if it is small positive, so then it will be this, and you will see that this peak would come when x b equal to half. Okay. Similarly, if it is small negative, it will be like this. Okay. And here also you will see that x b equal to half, fine, that minima would come there. Okay. So, this is I am plotting del H mix. Now, we can also say that it can be like omega, which can have positive, small positive or small negative value, because x a, because that is nothing but omega x a x b. Now, what would be its effect on delta G mix? So, that effect can be found out. Let us say I plot another here, taking this information here. So, let us take delta G mix when it is ideal. So, delta G mix when it is in case of ideal, so that will be nothing but minus T del S mix. Okay. So, I can have a plot of minus T del S mix, and del S mix is always a positive quantity, which is nothing but R, which is universal gas constant, x a ln x a plus x b ln x b. Okay. So, this would be always negative. Now, I can plot that minus T del S mix, this is minus T del S mix ideal, which is nothing but delta G mix ideal. Now, when we talk about non-ideal cases, let us say we take a small positive of del H mix. So, the non-ideal cases, so this is ideal, non-ideal, and case 1, what is that? That del H mix. So, delta G mix is equal to del H mix minus T del S mix, and this T del S mix is same as ideal. Okay. So, then if it is small positive and it is symmetric, so we will see that plot would, the second plot, which is coming due to the combination of this del H mix and minus T del S mix. So, this minus T del S mix, if you recall or if you have observed that condition is always helping to have a randomized mixing. But this del H mix, if it is positive, then it actually prevents randomized mixing over the entire composition range. Rather, it would always try to have similar atoms to have bonding. But if this value is small positive, so what we have drawn here, then the combination of this would actually make the del G mix to be negative all the time, but it will lift up compared to del G mix ideal. So, that plot would be like this. So, this is nothing but delta Gmix, let's say case 1. Okay. And this delta Gmix is basically delta Hmix is equal to greater than 1. So, this is case 1. So, this particular curve plot and this plot, that combination would lift it up. Now, if I take case 2, so where, and this case delta Hmix is greater than 0. So, case 2 is delta Hmix is less than 0. Using the similar logic, now since it is also negative, minus T del S mix ideal is also negative. So, the entire Gibbs free energy for mixing would go down compared to the ideal case. So, that plot would be this one. So, this is delta Gmix in case of case 2, and corresponding delta Gmix case 2 is here. This is delta Hmix case 2, fine. So, that minus T del S mix ideal, that would take the delta Gmix 2 to go farther down. Now, if I take only the Gibbs free energy for mixing term, leaving all the other plots, so that plot would look like this. So, this is again 0 0 0 0. This is in case of ideal, this is ideal. So, this is delta Gmix ideal, and the second one Hmix is slightly positive, fine. So, this is delta Gmix case 1, and the other one is fine. So, this is delta Gmix 2. Now, let us draw, and this is xb, please put all this thing, this is xb varying this way, xb equal to 1, xa equal to 1. So, if I try to draw, let us say at this composition, the tangent over that delta Gmix for all the 3 cases. So, here the tangent would go like this. Now, the second case, the tangent would be at this location, fine, and the third case where the tangent would be okay. Now, let me put some mark here, B, this is C, let us say this is B1, this is B2, this is B3, this is C1, C2, C3. Now, we can actually get the idea of del G mix bar of B in the mix and del G bar M A also. So, now, so we can write that. So, this quantity is nothing but delta G bar M B. This quantity is nothing but, so delta G bar M B when it is ideal, and this one delta G bar M, this is for case 1, this is for case 2, okay, of course for B. Similarly, on the other side we can also get those information for A. This quantity is nothing but delta G bar M A when it is case 1. This one delta G bar M A, or we can say delta G bar M A ideal, and the third one is here. This is delta G bar M A case 2. Now we can have a relation. Remember, all those values are negative in sense because it is starting from 0, because delta Gmix is, that curve is merging with 0 at the extreme ends, that means in case of pure metals. Now we can see that delta G bar M B, if I consider only in terms of B, for case 2, I am taking a mod value is greater than delta G bar M ideal for B, mod value is greater than delta G bar M B case 1. So in terms of B like that, in terms of A if we write delta G bar M A 2 is greater than delta G bar M B ideal greater than delta G bar M, it should be A when it is 1 and with the mod values. So these relations we are getting. In fact, from here we can also write RT ln AB case 2 is greater than RT ln AB ideal greater than bar RT ln AB case 1. Okay. So now AB is nothing but XB ideal, since gamma B ideal is equal to 1. So from there we can actually see, and in fact this can be also reflected over activity versus composition, and so this can be actually, now we see that from here we can write AB 2 is less than XB ideal is less than AB1. Okay. So we can actually see that gamma B2 is less than gamma B ideal less than gamma B1. So we can, so from here we can say that if delta Hmix is slightly positive, gamma B would be greater than 1, since this value is 1, and if del Hmix is less than 0, gamma b should be less than 1. So, these two informations we are getting out of it, but more importantly we are actually gradually getting into the equilibrium outlook or equilibrium goal between two phases, even if we consider del Hmix to be non-zero value, because there also this tangent method will be applied. And here from here we can also see how those are related to activity term now, because there it was simple, because we did not have to consider the activity coefficient gamma value. We expressed everything in terms of x A x B, but while talking about equilibrium between phases considering non-ideal cases, we cannot do it with respect to composition or a mole fraction, rather we have to consider activity term. So, everything will be expressed in terms of activity, because we see that this values are actually not related to straightway to mole fraction, rather there would be another excess term which is RT ln gamma of a particular component in a solution. Now, we have seen that if delta H mix is slightly positive and delta H mix is slightly negative. Now, negative, when it becomes negative, we see that the delta G mix shifts downward as we make more and more negative. So, that delta G mix would also fall down and it will become more deeper. So, what does it mean? It means that a particular phase for a see, everything we are doing it for a particular phase. So, if delta G mix has a very deep, very highly negative values, considering delta H mix to be highly negative, then that solution needs to be more stable. That stability would actually helps in, for example, a liquid has a situation that liquid of delta G mix of liquid as well as delta H mix of liquid is highly negative. So, similarly, delta G mix of the liquid phase will be also highly negative. That indicates that the liquid phase should actually try to be stable compared to any other phase. Okay. So, that consideration will come slowly. So, negative term is actually helping in stabilizing that phase, negative term of delta H mix. But if delta H mix term is positive, now at some point of time or at some values, not point of time, rather I would say some critical value of delta H mix, you will see that minus T del S mix, which is the ideal value, is becoming same when we talk about a mid composition x b equal to half, delta H mix value is exactly same as minus T del S mix value. Okay. That means they would try to cancel each other. So, if that cancellation happens and beyond that, you would see that the delta G mix would have actually a kind of upward trend rather than downward trend. So, that consideration we need to consider, but with that part we will do it in the next lecture, but first let us see what happens if we increase and decrease the temperature. Okay. So, in order to understand that, let us see with reference to ideal case first. Ideal case, which is delta G mix is equal to R T x A ln x A plus x B ln x B. So, if I try to look at, so this is x b equal to 1 or x A equal to 1, this value is also 0 0. Now, ideal case delta H mix equal to 0. So, the plot would be like this, and this is let us say T equal to T 1. Now, if we increase temperature, these term would not change at a particular composition, but because of increase in temperature this delta Gmix curve. So, this is delta Gmix at T equal to T1. So, now if we increase the temperature, so delta Gmix would again go down, fine. So, let us say the temperature has gone to, this is delta Gmix at T equal to T2 and T2 is greater than T1. Why? Because if I consider this particular term, this is negative at any composition other than pure metal side. So, that negative, so that means it will fall down, it will become more and more negative. So, if I increase the temperature, we will see that plot will further go down. So, this is let us say delta Gmix at T equal to T3. So, T3 is greater than T2, like that way it will fall down. So, that means that particular phase stability is going up and the system would like to be in that particular phase. But if I decrease the temperature, we will see that this plot will start going up. So, let us say this is, or we can say that this is delta Gmix at T equal to T4 and T4 is less than T1. Another plot we can do, let us say this is delta Gmix at T equal to T5, where T5 is less than T4. Now, you see that as we decrease the temperature, the stability of that phase is actually, mixing ability is always there, but the degree of mixing ability compared to higher temperature and lower temperature, that is changing. Okay? And degree of phase stability, why we are saying degree? Because we are also saying that the free energy line is either going up or going down compared to another one at a different temperature. For example, if I try to look at this composition, let us say I am putting this composition and x 0 let us say in terms of B. So, this is x B in terms of B. Now, I see that I can actually have mixing free energy hierarchy. Okay. So, we can say that delta Gmix at temperature T3 is less than, if I, or we can say mod value, because these are all negative value, is greater than delta Gmix at T2 greater than delta Gmix T1 greater than delta Gmix at T4 greater than mod delta Gmix at T5. Okay. T5. So, now we see that gradually if I start from a very high temperature to low temperature, gradually the particular phase formation ability in terms of delta Gmix is actually the degree of formation is actually reducing as we decrease the temperature. So, that means increasing temperature in case of ideal mixing would always like to have kind of better formation ability. Or if you look at other way around, we have said that when gamma of a particular phase, particular component, let us say B, is greater than 1 or less than 1, in this case with increase in temperature, both cases if we increase temperature, so that case, this case gamma B would actually reduce, this case gamma B would actually increase in order to achieve ideality. What does it mean? That the mixing becomes more and more random. So, that is what I wanted to tell you, that with increasing temperature mixing becomes more and more ideal. Okay. So, this is I am talking with respect to ideal mixing, but The same can be reflected even if we consider delta G mix, delta H mix to be positive. Of course, delta H mix to be negative, this would all this particular delta G mix curve will always go down, okay, more and more negative. But the problem happens or the confusion happens with respect to delta H mix greater than 0. So, that time with increase in temperature, since that has a strong effect on delta G mix to become more and more negative. So, the entire stability would actually become more and more feasible for that particular phase as we increase temperature, because it will try to be more randomized, and that happens because every system would like to achieve ideality with increase in temperature, and that happens due to the Gibbs free energy of mixing hierarchy situation. So, let me just stop here. We will consider the condition for when it is ideal, non-ideal. Okay. So, we have done it with ideal case, and remember here it is basically delta G mix plot. Remember, and previous cases also, if I have not done it, please do it. This is delta G mix plot with composition. So, now here we will try to look at non-ideal cases. We will try to see temperature effect when delta H mix is negative. In fact, we will also consider the same temperature if we try to increase the positiveness of delta H mix, what would happen to the delta G mix. Okay. So, let me stop here. We will continue our discussion in our next lecture on the same topic. Thank you.